All right, everyone. So we're welcome to the lab session for our Qiskit 4 Fest event. So now we're starting with these fundamental labs. Then we have the instruction to read the explanation for each concept, to complete the coding exercise in the designated cell. Then we can always check our answer in the solution notebook. So after today's session, the solution notebook will be available to you. It's just for you to practice. And then here we want to work alongside together to be able to solve or work with materials like this. So also, if you have people who are yet to join, we can communicate to them to join us. So the first line here with the exclamation mark is because you are having the Jupyter notebook. So if you want to install Qiskit, if you don't have it installed already, that is what the first line is doing. So it's going to install Qiskit visualization. It's going to install Qiskit IBM runtime. It's going to install Qiskit AER, and then the importation of the calcium theorem. The first thing is that if you are running this particular cell for the very first time on your machine, it might take long because you are going to be installing for the first time. But if the installation has been done before, it's not going to take long. So at the same time, it is importing necessary tools that we're going to be using for this section. So now it's trying to install things that I don't have on my machine. Then this installation is done and is completed. Like I said in the last session, no, sorry, it's not completed. It's going to be, you will know if it is completed when you have a number in this bracket. So the installation is still ongoing. It is not completed. Here it's saying successfully installed. So all the installation I think is completed, but then the importation also just got completed. So the first cell ran with no issue, with no error. So you're good to go. Now to the next cell, the explanation is that we have the poly operators.
Hello,
Yes.
I think you are running faster than us.
Oh, if it is very first time you are running this installation, it's going to take time. So that's what I said earlier. So
Well, the file you are using, we have not opened it here.
oh,
Please hold on.
okay, then I would wait. So if there's any challenge to open it, please let me know. So it's just for us to be able to follow, especially for those of us who have a Qiskit installed in their laptop or on their machine. So please let me know if there is any challenge with that, so we can follow through.
Sorry, Victor. The Qiskit is it to read those files you sent? Because I have Jupyter. Jupyter, at least you can run these commands there,
Yes, you
right?
can run the command directly on Jupyter Notebook. So if you don't have Qiskit installed before, that very first line will install Qiskit for you. So you can just install directly on Jupyter Notebook if you have it installed on
O-
your machine. So, but
Okay.
you can proceed. Just upload the file to your Jupyter Notebook, then run the first cell. If you have any error, let me know. Then you will be permitted. You can share your screen, then I can guide you through.
All right.
So the essence of this session is to have us work together, like it's hands-on. So if you have any challenge, please do not hesitate to let me know. Either with the installation, with the uploading of the files. If you already have like a Jupyter lab environment, you have never installed Qiskit, you can do that just by the first line. It's going to install everything that is necessary. But note that it's going to take some time, and also I don't know the amount of data that it might consume because it's going to be downloading some new stuff.
Sorry, Victor,
Yeah.
the The lab that you're showing on your screen, the one that you're sharing,
Yes,
I can't find it on the drive.
it's the Qiskit Fundamentals, just Qiskit Fundamentals lab.
Okay. You renamed yours. All right.
Please check that is the same as the one I mentioned.
No, sorry. Do I need to run my Anaconda before? I think I can just.
What exactly are you doing at the moment on your machine? Do you have access to your Jupyter environment?
Yes, yes.
Jupyter
I've
Lab
opened it on the browser. So,
on the browser. If you're opening it on the browser, you will not be able to run the code. I mean,
okay.
because you have to have it installed on your system. That is where Anaconda might be useful. So if you have Anaconda, you can open Jupyter Lab directly from Anaconda. So all you need to do is download the Jupyter notebooks, then upload it to the Anaconda, or you open it from Anaconda, whichever one works.
Okay, I think I have it on Anaconda. I can't.
I
I have
think
to.
I'm not sure if Google Colab still support Qiskit, but the platform that is online that supports Qiskit is QBridge. It's right here on my screen. I'm not sure if the screen is showing that. Um,
Because I didn't install it, so it's launching it on the browser. So my
what I'm
system
saying is, if
saying
you want to do anything on the browser, you can use QBridge. So QBridge is the online platform what's it called? That Qiskit recommends.
okay, yeah, Qbread. Can you spell it?
Yes, it's just on my screen now. Sorry, I'm not sure if this is showing on my screen. Is the screen changing? Because I'm not sure.
No, it's not changing.
It's supposed to, because now I'm not observing the change of screen. Oh, okay. Now I stop the share. Never share again. Okay, do you see QBridge now? This is QBridge. So you can just go to QBridge. QBridge is the accepted platform from Qiskit. So Qiskit is directly installed here. So what you need to do is, once you come to the link, just qbridge.com. So um, when you launch QBridge, I think you need to have an account. So you might have to sign up for the section, so that you can launch the lab here. Yeah, so you need to sign up. So you just create an account. Once you create an account, I guess I have an account with them. Then once you create an account, I'm not sure what my password is now, because it's been a while I used the account. I am not sure this works. Wow. I remember my password. Okay, so what you do if you are able to get yourself signed up, continue to dashboard. Oops, I did not agree. Oh my God. So this is just an alternative for those who might just want to do everything directly on the web. Continue to dashboard. Agree. Thank you. Then what you need to do, like you can just use this Qiskit Global Summer School session because this has been updated and we have the updated Qiskit on it. So are you following?
Yes.
Yeah. So just sign up for it. Once you sign up, then you use this Qiskit Global Summer School lab. You launch it. Then once you launch it, it's asking you what machine do you have. I think it's not available. Oh, so too bad. Then you can use the default workspace then. Free, this is sufficient. I'm doing job online. I think you should have a free access. I don't know why this is not working. 0 credit per minute. Yes, Intel blockade. I don't know. This is not. Should be able to launch a lab session from here. It's been a while I used this platform, so I cannot really tell if I'm doing everything correctly. Plan, yeah, it is free. Copy IP address should be locally. This is not allowing me to launch the lab, even though I have like 5 gig free space, quantum devices. Maybe I check. So those that have their local system. I hope everybody is now at the same level. While I'm trying to look for a means to sort those that we want to follow through online. UIQC 656, it is free. I don't know, I'm unable to launch my lab. I don't know why. Lab session is not launching. I really do not know why. If you have VS Code, that's another option you can explore.
I think it's giving me Python 3, hard environments, QGSS, quantum dots.
Once you can launch the lab, you are good to go.
So which one do I pick? Is it Python 3? Or I should go to quantum docs?
Just choose Python 3. Everything is built on Python.
Python
Just
3.
some other section that is built on Rust. But we know that.
Yes, I think I'm able to log in.
So once you are able to log in, then you need to find a way to upload the material to the page. That's all you need. You downloaded material already. Just upload it to the platform. Then you can. Please, I think your mic is on again, Daniel. Okay. So from the other participant, can I proceed? I need to proceed now. So I think the best thing now, because we are going to have access to all the materials, I mean, both the lab work, but it's just good that we work side by side. But if we are not able to, because we need to move forward so that we make the best use of the time. Okay. So so for those that, so do you confirm that I can proceed? So we are here now, so I need to proceed with this.
Yes, you can.
Okay, okay. Thank you. So um, sorry, one moment. Um, okay, so for us to proceed here, we are to create a three. Let me continue the recording session. Okay, thank you. And set the line. So here we have to create a 3-qubit poly operator that is representing Z on qubit 2, Y on qubit 1, and I, the identity on qubit 0. So if you can see my screen, okay, so if you can see my screen, the pattern is this way. I'm going to try and Okay, yeah, I think you can see what I tried to write. This. So the pattern for the code, the poly operators is more like where you have 3 qubits. Say you have qubit 1, qubit 2, and qubit 3. So you have Q1, you have Q1, you have Q0. Sorry, you have 3 qubits. So 3 qubit will mean that we have Q0, Q1, and then Q2. But the order of arrangement is always that, because if you look at it here, we have the poly X, we have the Xi. So the note gives us the idea. So if you look at this, so this is the way to get the solution. So it says you can also construct multiple multi-qubit polys by specifying characters for each qubit, e.g. Xi for identity on qubit 0, and then X on qubit 1. Is this clear?
Please repeat what you said.
Now, what I said is that you can use this line to understand the question. For a single qubit, all you need to do is to put poly, then X gate on, that is what you need. But 2 qubits, you need Xi. So X here will be on qubit 1, and the I will be on qubit 0. So for our operation, you have to create a 3 qubit poly operator. So we can call it poly op. So poly op for the poly operator. Then how do we write the operator? We take advantage from this we take an idea from this solution here. This is for a single qubit, S gate on that single qubit. So following that procedure, all I just need to do is I'm going to write poly. So now I'm designing for 3 qubits. So which means that I'm going to have the gates in sequence. So Z on qubit 2, Z on qubit 2, Y on qubit 1, then identity on qubit 0. Is this very clear? Do we get the first exercise? This one.
Can you go over it again?
Okay. Now, if you look, if you read, there's already an explanation because it's meant to be self-explanatory. The explanation says the operators that we are concerned with, that we call the poly operators, they are the X gate, Y gate, Z, and high. The high is just the identity operator. So if it is for a single qubit in Qiskit, you have the poly class. This is the class you call on, like a function. Then you put in the operators that you want. So here you are putting in the X operator on just 1 qubit. So if you want to construct multi-qubit polys, you can specify the character, for example, Xi. So X will be identity, I, the last one to the far right, is the identity operator on qubit 0, and X is on qubit 1. So following the Qiskit little endian bit ordering. So the little endian bit ordering is that the ordering starts this way. You have 0, you have 1, and you have 2. So this is how the ordering goes. So ordering goes from the little endian. I explained it some time ago. Little endian means that the least significant is to the right, and the most significant is to the left. So this is the most significant qubit or bit, the qubit, then you have the least significant bit. So this is like the least, so this is the 0 qubit, the 1 qubit here, and the 2 qubits in this order of arrangement. So did we get this? So following this idea, then you can create your new poly operator. So you call on the class, which is the poly class, this one. Then you design the multi-qubit operator. So here you are saying that you want identity to be on qubit 0, Y to be on qubit 1, and the poly operator Z on qubit 2, just as the task that we are asked to produce. Can I proceed?
Question.
Yeah?
Identity represents X now.
No. Identity is the high. I is identity. Like
Okay.
this is the task. We are to create a 3-qubit poly operator representing Z on qubit 2, Y on qubit 1, and I, which is the identity, on qubit 0. So it's just to
Okay,
follow
no
that
X.
ordering. Z, Y, I. Then the next thing is to print the operator. This is just a Python command. So we print the operator. So our operator that we have designed is called poly op. Now it is not a string, so we don't need to put it in inverted comma. So the third thing says we are to print the matrix representation. So if I just run this command, it's just printing it for me that I have successfully written Z, Y, I. But this is not the matrix representation of this poly matrix, a poly operator. So the matrix is that the class. So to know how to write this in matrix form, you have to go to Qiskit documentation for the poly class. But now we assume that we have read the representation, the documentation. Then what we need to do is to print. So now, because you are printing, the matrix operator for the poly operator is you call on the operator class. Then the command to change it to matrix is to matrix. So it's a method. So in operation in Python, so this is a method on the class. So it is something that determines how the class should behave. So polyop is the name of the operator that we have designed, which is a class in Python. Then dot to matrix is the instruction we are giving to the class that converts this operator into a matrix form. So in this way, then we have, if you just run it this way, the last command is what will be interpreted. So this is the way it looks like in the normal matrix form. But because this is an array, we can just use the print command to print it directly. So this way you have, so the second print is this. The first one is ZYI. Then this is the matrix notation for the operator. Now, if you see the way the matrices are written, it looks somehow ununderstandable. But this is Python lists format. So this is array. So this is the first row. If you count, you have 1, 2, 3, 4, 5, 6, 7, 8. Then down you have 1, 2, 3, 4, 5, 6, 7, 8. So this 8 by 8 matrix as expected, because for each qubit 0 or 1 you have 2, then 2 raised to power 3 is 8. Do we get this? So if you want to interpret this, this is 0 plus 0j. J is the identity. Sorry, J is the form for writing the complex number high. So this is like 0 real plus 0 imaginary. So where you have 1j, that is 1 high, or 1 like a spot where you have this section. So this is odd imaginary I. So 0 plus 1j. So this is just the interpretation of the matrix of the operator we have just defined now. Is this very clear?
Well,
Sure?
I want to clearly get this. Now, this is an 8 by 8 matrix, right?
Yes.
And all the elements are complex.
Yes, they are all complex numbers.
So there will be 64 elements.
Yes, yes.
So the first one, 0, 0, is 0 as x plus 0 as y, j.
Yes, so it's simply 0.
So the same representation like that for all through.
Yes.
Now, going back to the code, I mean,
Okay.
how can we really interpret the code to the matrix? Because
Interpret.
by default, it brought 8 by 8 matrix.
Yes.
Could he have brought a 2 by 2 matrix
Uh,
or 4 by 4 matrix
no,
or
no,
something
no.
like that?
This is what is going on. We have known this before in the explanation. So we have the Z, we have the Y, and we have the I. So each one of them, they are 2 by 2 matrices. So it is the combination of the three together as a single operator. So that makes it 8 by 8. I think I remember explaining this, the tensor product. So it is the tensor product of these three operators that led to the matrix that we have as the final matrix. Do we get this?
So in that wise, we mean 2 by 2 would mean for Z 2 raised power 2, 4 times 2 raised power 2 for Y, 4 times 2 raised power 2 for I, and that makes 4 by 4 to get 64. Is that the picture? Because when we did the theory and we are doing the tensor product, we actually put each of the matrix in the larger matrix. For example, yes. Yes. Now, in this case, to get a 64 element matrix, if I pick the first 2 by 2 matrix and the first element there is A, or let me say A1, or okay, let's use Z1, Z2, Z3, Z4. The other one, Y1, Y2, Y3, Y4, and the last one. Now the tensor product will now mean that the Z will be replaced by each of the Y's, bringing the matrix in them. Likewise, the I. I want to get a very clear picture of this.
Yes, let me just do a
Tensor
sample
product.
tensor product that we learned some weeks back. So let's say this is what we have, and we want to have a tensor product of these 2 by 2 matrices together. So the idea we developed was that the whole of this matrix, we multiply each location of the other matrix to give a bigger matrix. So we're going to have here a 4 by 4, which is this matrix on the position where we have 1, on the position where we have 2, sorry, another 2 by 2, like multiplying all the 2. Then you have all of this multiplying 3. Then you have this multiplying 4, which means that along the row you have 4 elements. Then down the row you have 4 elements. So this is a 4 by 4 matrix. Is this understood?
Yes, this is understood.
Yeah. So by the time you now join the third one again to this one, another tensor with it. So let's say we have another 4 points. So each of these points will be multiplied further. So that is where we have the entire 8 by 8. So it's just the math, the dirty math that has been done just with the code. So is this understood further, or I will explain it again?
Well, I'm not the only one. People are not commenting.
Okay, so the idea here is just for you to be able to write the matrix that you want, any combination of the poly matrix. Maybe you have 10 of them, you have 15 of them, you have 4 of them, you have 3 of them. So here we have 3 qubits. So we want the poly operator to work this way. So, and that is what we have just we have been able to design our poly operator, and not just design it, we are now able to visualize it as a matrix. Okay. So another thing we are going to do now, as we move on to the next part of our work, is that, although we don't have time by our side, so here the explanation is the first thing we need to read through, because you're going to have access to this. You can work on it on your own. So now here we are looking at single qubit gate and faces. Now single qubit gate and faces. So the single qubit gate, we have example of them like the S gate, the Y gate, the Z gate, the Adamat gate, and the S gate. So this S gate is half of one of the other. You also have the T gate. Okay, this is even here. You have the T gate. So they are rotation matrices. So here, S and T are the phase gates. So you can use them to create any phase. Now, when you say phase, it's like a rotation. So the S gate adds a pi over 2 phase to the state 1. So what it's simply saying here is this. When you say a phase gate, you remember the Z gate. So here, the Z gate will act on 0 and make it 0 still. But the Z gate will act on 1 and change the phase of 1 to -1, 1. Do you remember this?
Yes.
Okay. So what this Z has done is that Z has changed the phase of 1 to -1. But here, -1 may not be understood as a phase flip, though we call the Z gate the phase flip gate. But what happens here, again, is for us to think carefully about the Argand diagram, like we were taught in basic linear algebra, complex numbers. So we have the real part here, we have the complex part here. So here we have the real to be 1, we have the imaginary to be I, here we have the real to be -1, and we have the imaginary here to be -I. So with this, if you move, this angle here is 90 degrees, so which is pi over 2 rotation. This is what we mean by the phase. So, but if you come here, this is a 180-degree shift. So what Z is doing is Z is applying a pi phase to 1, because the value of the phase flip at pi is -1. So that's the -1 that we're having here. Then if you have like for example, now the S gate is adding a pi over 2 phase to 1. So it means that when I have X acting on 1, then what I'm going to have in this case, S acting on 1, will be what, from what we have seen now, it's going to be the phase of pi over 2. And the value of pi over 2 at that phase is I. So it's going to change 1 to I1. Does this make any sense?
Yes, it does.
Okay, so then the T gate is half of the S gate. It's going to make it a phase of pi over 4. So pi over 4 is just in between 1 and I. So by the rule, it's just going to be the in between 1 and I, the value there, by the time you do your, what's it called now? By the time you do the combination of the two using the proper mathematic approach, you're going to have the combination of 1 and I at the value of pi over 4. So this is what the phases means here. So it's just rotating it along the, what's it called? Along the axis. All right. So now
can we distinguish which of the pi over 4 we mean? It will be between I and pi over 2, or pi over 2 and R.
Sorry, what it means is just e to the power, because if you remember the way we wrote the, the complex number is always written this way, e to the power of I theta e to the power of I theta. This is a complex number representation, but what we have according to our structure of the qubit, if you remember one time we explained our qubit that we can have this plus beta 1, then we say both alpha and beta, they are a complex number. So, but this beta here is represented with this value here, this guy here, such that we can always write the phase value. So the phase value here is now e to the power of I. So whatever the angle we have, let's say we have pi over 2. So we can easily determine the value of this e to the power of I pi over 2 from the Argand diagram, which I showed earlier. So because we know that this is representing cosine of the angle on the real axis and what is it called? Sine of the angle on the complex axis. So we know that if it is directly I0, it's going to be directly all on the cosine angle, which is cosine of 0, which is 1. But if it is 90 degree, we know sine 90 is 1, so it's going to land directly on the I-axis. This is just all that we learned or we looked about, we talked about. But when you have it at pi over 4, all you just need to do is to express the value of EI pi over 4. And whatever that value is the value of the coefficient here, which is what we refer to as the phase. And this is why the phase always affects the one qubit, the ket 1. For the 0, if you can see here, it's always leaving the 0 component unchanged because phase only comes in the mathematical representation of the qubit 1. Okay. So we also have a global phase, but it's not it's negligent in the explanation of all of this. So the goal here is how do we now represent this in the labs in the code form. So I think we should just focus on the lab session because we can always do the math. If any of the math is not clear, we can always go over it again during the session for theory explanation. So here we are to create a quantum circuit that contains 1 qubit. In the last section, I taught us how to create a quantum circuit. You can give it any name. So are we still following?
Yes, but
Okay.
I want to ask, this worksheet will be given to us.
This current one, yes, you're going to have
So we don't need to be trying as you are doing
no,
it
you're
now.
going to have the solution. All the solution will be made available.
Okay.
The practice phase. So we're just looking at it together. Why is this the way it is? Instead of us reading the solution without having the understanding. So this is you create the quantum circuit by calling on the quantum circuit class. Then you put in the number of qubit you want to create. So it's 1. We have done this before in the last lab session. Then put the qubit in the state 1. So what's the idea of putting the qubit in the state 1? When you create the qubit this way, the circuit this way, the qubit is automatically initialized in the state 0. So how do we put it in the state 1? You apply which gate to flip from 0 to 1? So anyone, what gate do we apply to flip from 0 to 1?
AND gate.
Sorry? Did I hear AND gate? It's not classical logical.
Sorry.
Even if it was to be classical logic, it would have been the NOT gate. NOT gate is what changes maybe 1 to 0 or changes 0 to 1. Do we get this? Hello?
We are together.
Okay, so what is the how do I put it? What is the equivalent gate that converts 0 to 1 or 1 to 0? This is supposed to be bonus by now. We have done it in the talk sessions now. You say it's flipping from 0 to 1 or flips from 1 to 0. Okay, we have all of these gates here. This X gate, Y gate here, Z gate, Adamad, and S and T. So which one of these gates will flip from 0 to 1 or from 1 to 0? Other participants do not want to answer the question. You can unmute yourself and answer.
Okay. To fully get something.
Okay, it's the S gate. I believe we have discussed this over and over. So the S gate will always flip from 0 to 1 or from 1 to 0. So all you need to do is to do X on which qubit you want to flip. Since there is only one qubit, then you say qubit 0. Don't forget the count of the qubits start from 0, 1, 2 to the next one. Then the next thing, question 3 says, add a single gate to the circuit that applies rotation of pi over 4 phase shift. So as you can see here, it's already in the explanation that it is the T gate that had a pi over 4 rotation. So T gate is what we need to apply next. So Qt dot T, then you have 0, then you move on because this will do the job for you. S gate flips it into state 1. T gate applies the pi over 4 phase shift. And what other thing do we have? I think Daniel is okay. So T gate flips it. Sorry, T gate applies the pi over 4 phase shift. Then the next thing says output a Dirac notation representation of the circuit state vector. So this we have not done before, but let's take it step by step. First thing is, let me see if what I've done makes sense. I can draw the circuit to see it. So this is the command qc.draw. This is not so fanciful, so it's just saying xt. So like this is my qubit, I've applied x to it, I've applied t to it. But if you want to see it in a more fanciful form, I can say give it to me in using matplotlib. So matplotlib gives you a more fanciful design, which is this. You must have seen this before. Then another way you can then request for the draw, you can show in latex form. No, sorry, this is for state vectors. So for me to show it in latex form is like I want to write it the same way we usually write it as what's it called, as maybe ket 0 plus ket 1. So that one, what you need to do is to have a state vector. That is, you write it in vector form. So if I want to convert this entire circuit into vector form, so I call on the class called state vector. That's the name of the class. Then I put my circuit in it, QC. So I can just say SV for short form, SV like state vector. So instead of now, my circuit is no more QC. It is now a state vector diagram. So I can say, give me the diagram. Now I'm no more using matplotlib. So I'm using latex. Give me in latex form. So latex is going to write the normal matrix form that we know, as you can see it here. So this has given us in the normal mathematical transformation that we know. So one thing we can learn to see one after the other is this. Sorry, are we following?
Yes.
Okay, so what I want to do currently is I've commented out qc.x. I've commented out the T gate so that we can see the transformation line by line. So when I created the circuit originally, it is in the state 0. Can we see it? So let me give it some name. SV. Let me give it name. Prefix equals SV. So let me just call it circuit state vector. So this is bad writing form. So the circuit state vector at the start, as you can see, I don't want to give a name that is state vector for my circuit. CUIT. Okay, so at the start, the circuit state vector is 0, ket 0, right? This is clear, right? So the moment you flip it with the S gate, so this is what you are doing now. So now X gate has been applied, but we have converted it to state vector. So when I show it now, it becomes 1. Are we following?
Yes.
Okay.
But I want to point out
yes,
that it is seems to be very good to be good with Python code before working on Qiskit. The reason is this: the circuit is a keyword, is in red, and is in brace bracket. Now,
Okay.
the code sv.draw with the bracket to call the function in there, I think follows the Python regular code of writing. So that's why I think I need to ask that to get that clear.
Okay. Yes, I agree that the whole of Qiskit is built on essentially Python. However, taking the Python, yes, there's always the need to have like a basic background of Python. But one of the things I've learned with coding and I'm still learning is that while you are working with a particular platform, as long as you learn to use the syntax, you can develop the knowledge from there. It's just to observe how the whole thing works. Like I said, everything I've written here has been explained in the Qiskit documentation. I didn't I want to go to the root of, I don't know how Qiskit was written, so I have to go to the documentation to check. Everything is written in the language of Python. However, what the purpose of this hands-on is that when we see it being used, we can begin to gather, like it's just like a vocabulary of words. So we can begin to gather vocabulary of words, not just the words, because some of these design now, they are only restricted to Qiskit because all of these are built already. So where Python comes in is for you to know, okay, what Python tool or what Python object is this? Oh, like I said earlier, that this quantum circuit now, for example, is a class. So Python has what it means to be called, to say something is a class. Sometimes you can say this is a list. Sometimes you say this is a tuple. So all of these are just basic things that we can pick up while we are learning the code. So that's why I will keep talking about it. Okay, this is a class. We may not understand everything that is a class in Python, but just know that, oh, when I have a class, this is how I use it. One of the things you know about a class is that, for example, now everything here from quantum circuit 1 is a class. I have given it the name QC. So this QC is representing everything as quantum circuit. The dot, whenever you have a dot after a class, is more like a command that is changing the form of that class. And that is why I'm trying to show us the change, is that when I first created QC like this, so knowing Python is for me to say when I put hash, that line is not going to be read. So that's a typical Python rule. So when I run the code, the line that wrote state vector means that I converted the circuit into a vector form so that I can read it vectorially, like ket 0 and ket 1. So the diagram that I'm drawing here, that is this state vector itself, is another class. So I mean, I'm now instructing that this vector should be given to me in a fanciful way. That is the draw method that is here. So drawing it now, what platform am I using to draw? LaTeX, those that are familiar with research and academic writing, LaTeX is what you use to write most of these mathematical tools. So LaTeX has been built into Qiskit. So that is why I'm able to see the ket written in a nice way here. Then the preface is just to give it a name. And the name I gave it here is also a pattern of writing in LaTeX form, which is this state vector circuit. So all of this is just for us to observe as we learn in using the code. So, but the focus now is just for us to see how some of these things are done in Qiskit. So now, because any question?
Yes, just to quickly mention that the LaTeX that you called to prefix with the circuit, now the underscore follows the rule of LaTeX writing. So that means what you wanted to write in LaTeX is what you have stated in front. That you should prefix the, I'm not seeing that very well, SV underscore circuit. And that's why it plays circuit with the underscore. You understand?
Yeah, that's the normal LaTeX.
Okay, okay. I want to just get the code clear so I don't get a
Yes, I
have a mix up.
understand, but yes, I think it's step by step, because I may not be able to explain all the rudiments in each of the steps, but just for us to see that, oh, this is what this line is doing, this line, then we can now, so when we are doing our personal tweaking here and there, we can try and change it, and what will happen if I do it this way? So that's how we learn also, but the documentation tells you exactly how it is done. So here, after adding the X gate, if I run it now, we see that the circuit has changed to 1. Then after adding the T gate, of course, the Adamant gate that we know, if I put H here now, you will see that it's already in the Adamant gate. Like it's now like in a superposition of 0 and 1. Now, the way the the code has been designed has been designed to always rationalize the sword. That's why you're having the sword in the rationalized form. It's not the usual 1 over root 2 that we usually write. So this has been rationalized. So, but then to follow our task, it says the S gate, we have done that. Then the T gate. So applying the T gate, we apply a phase to 1. So this is the phase. So this is the value I was talking about earlier. This is the value of e to the power of high raised to power e to the power of I, this number, e to the power of I pi over 4. So the solution to this is just exactly what we have in front of 1 here, to show that the phase is actually shifted to the value of pi over 4. And you can easily verify this with your, what's it called? You can easily verify this with the Pythagoras theorem. What's the value of cos? This value, because the answer to this is just cos pi over 4 plus high sine pi over 4. And pi over 4, we know is 45 in degrees. That is root 2 over 2. And that's why you're having it just here. I think the math is clear. But yeah, I don't want to be doing much of the math. It's just to write the code. So that's what we're doing now. So I hope this is clear. We can visit it again when we work on our own. So just the fundamentals. Okay, and also the next one. So the third one is saying that we should what's the task? So now we have other gates that we have different from the single qubit gate. Like these are sorry, I think my screen froze. So here we have the single qubit gate. So here now we are now looking at more gates that we call Rx, Ry, and then Rz. Now, what is the meaning of this gate, or where does this gate have meaning to us? The meaning of the gate is very simplistic. Let me show you. When you have the block sphere, we have discussed this in the theoretical session. We explained that the block sphere is designed along the, and I have a different column. So we said that the block sphere is designed along the z-axis, we have the y-axis, and we have the x-axis. Okay, good. So the rotation gates, so this is the z, the y, and the x. So if we follow through with the z-axis, so this is where we have the Pauli z operator in the basis of z gate. So you can say this is your 0 and this is your 1. But in the x basis, we always have plus. Then if you follow it to the other end, you have the minus. So this is in the x basis, we have plus and minus. Then in the y basis, you have I1, and then I think minus I1. I hope I'm correct about this. I'm not so sure. Maybe 1 plus I or 1 minus I. So I can't correctly remember what is there, but it's either I think it's 1 plus I and 1 minus I. Yes, those are the coefficients. But the goal here is that each of these lines produces an axis of rotation for your qubit. For example, if I have my qubit originally on the Z gate, that is this axis, if this is where my qubit is already, so you will agree with me that any arrow that is already pointing around this axis if I try to rotate it around the same basis set, around the same axis, it will just remain pointing in that same axis. Do you get the illustration? That is, it's more like holding up a pen, and then I keep rotating it along the same axis. So it is still pointing in the same axis. The rotation just remains in the same way. The direction of the arrow just remains the same way it has always been. But consider if I try to rotate it along the y-axis. If I rotate it along the y-axis, what I'm simply doing is that the point will shift. So the arrow that is pointing up and down will now point into the screen and out of the screen, because I have, if I rotate it completely at, say, 90 degree along that y-axis. But if I choose another axis of rotation, then I can make the rotation happen in such a way that this up and down location is now pointing left and right. Do we get the idea of the rotation? So depending on how you rotate, so the rotation gate is the RY, RX, and RZ. So you are rotating either along the x-axis, or you are rotating along the y-axis, or you are rotating along the z-axis. Is the physical meaning of this gate clear to us now? The RX, RY, and the RZ. Can I get
Yeah, no. Yeah,
Yes.
Okay, good. So, but then another clarification that we must now bear in mind, which most people don't bear in mind, is that this block sphere is deceptive. Ideally, when I look at the z-axis and I say this is 0 and this is 1, it's deceptive in the sense that because of the physical representation, it's giving me an idea that the separation between 0 and 1 is a 180 degree. It's not true. It's just for the representation of the axis. We are only using the axis to represent that this is the z basis. The original thing that happens is that for every theta that is the separation angle on the block sphere, the true angle is theta over 2. I believe this should be clear also. So for every angle you can see on the block sphere that is visible on the that is physically realizable on the block sphere, the true angle from the mat is actually half of that angle. So that said, it will therefore mean that whenever I use the RX, or I'm to use the RX, RY, and RZ gate, I must be very careful of the value of the angle of rotation. So let's read this again. The gates perform rotation around the axis of the block sphere, so creating superposition states. So a rotation by, now this is what I just explained now, a rotation by an angle theta around the y-axis on an initial state 0 produces the superposition cos theta over 2 and sin theta over 2. So you can see that the rotation actually happens by an angle of theta. But in the mathematical representation, it has been given the value of theta over 2 and pi over 2, such that for every angle theta that you make rotation with, you are always having the actual representation to be half of that angle. So I hope this is really clear. So now let's go to the code section. So the first one says we should create a quantum circuit that contains 1 qubit. So by now, this should be like something easy for everyone to do. So just call on the quantum circuit, then 1 qubit, just one, put 1 in the bracket. So then the next thing is apply a single gate to qubit 0 that is initially in state 0 to create a superposition where you have the probability of measuring 0 to be approximately 14.6% and probability of measuring 1 to be 85.4%. So in this approximation, how do we think about this? Don't forget, just by the course of illustration, when you have your cos theta and your sin theta, these are the probability of zeros and ones. So this is just what we are asked to do. So the goal here is that 14.6% is approximately 15, but then let's say 14.6. So 14.6 probability for 0 will mean that what we are saying is that cos square of theta over 2 is equal to 14.6%, y sine squared. Don't forget that this is the interpretation of the probability of theta over 2 is equals to 85.4%. So this is what we are asked to do, such that to solve this, you can say that your cos theta over 2 will be square root of the value of 14.6%. Then you can then find the value of your theta over 2 by saying the arc cos of blah, blah, blah. I think we understand the maths. So then whatever value of theta from here, so how do we then make the rotation? Don't forget that when we do a rotation has to do with the theta itself, not the theta over 2. So what they're asking us to do is to just find the angle of rotation that will yield the value of 0.146. If you do the cos square theta of that value of pi over 2, is cos square half of that angle, you're going to have 0.146. So I think the mathematicians can solve this approximately. So let me see, is there a mathematical tool? Let me try and use my calculator and find what is the nearest angle in radian. So, well, if you do this, which I don't want to bore us with the math, we have mathematicians here. So the required angle would be for me to apply a rotation y gate at 3 pi over 4. That's the 3/4 of the angle. Since if you look at the probability, it's almost like 3/4 of each of the value. 75 to 25 is am I correct? 75 to 25, yes, almost along that
Three
range.
quarter, 1/4.
So, sorry?
That's 3/4, 1/4.
Yeah, 3/4, 1/4. So I'm trying to, yes, 3/4, 1/4. So that's more like an approximative value. But then if you look at it in terms of the rotation, 180-degree rotation, we flip it entirely to the other end. So which means that if you want to have in this angle theta over 2, if you want to have everything to be 0, that is, we must have the coefficient to be 1, right? So everything to be 0 will mean I have to flip this at what angle? Theta over 2, what cosine of theta over 2 will give me the value of 1 so that I can have the probability to be 1? You agree with me that it is only cos 0 degree that gives 1, or in the other case, yes, cos 0 is what gives you 1. So it means that you don't flip it at all. Then here, sine 180 degree will give you the one that you're looking for. Sine 180 degree sorry. 180 degrees over 2. So the angle 180 degree is the angle, that's what I want to show, is the angle that gives us the complete shift from 0 to 1. So if I want to have somewhere that is, so this is what we're saying. So if I'm going from 0 to 1, I have to move completely 180 degrees. So if I complete 180 degrees, I will move to 1. If I don't complete 180 degree, I won't. So if I want to get to probability of 14.6% on the 0, so that means I don't have to move up to the 180 degree, then 85.4% of being in 1. So that means 85.4% of getting to 1. So it is somewhere around here. So I'm not yet up to the 180. So it is somewhere close to 180 degree that I can have 85.4% of being 1. Is this making sense? Is anybody there?
Manageably.
Manageably. Okay, let me go over it again. So what I'm saying is this. when you look at, this is just like the linear representation. If I want to rotate from 0 to 1 using the RY from the explanation that I have, it means that I have to flip from, because the angular, the mathematics explains it, that for me to have entire 0, cos theta over 2 and sin theta over 2 explains the rotation. So here, for me to have this value to be 1, it means that my theta must be 180 degrees, or what you refer to as pi in radian. So what I'm saying is that if I can shift from 0 to make everything to become 1, I must have moved the total angle of 180 degrees. So that means that this angular representation shifts me closer and closer and closer to the value that I'm interested in. However, if you look at this 180 degree is just sine 90. So it's just like the distance from 0 degree to 90 degrees. But in terms of rotation, it is up to 180 degrees of rotation. So what we are now saying is that if I need 85.4% to get to 1, so it means that I'm somewhere close to this 180, but not up to 180. Since that is because as the angle increases, because the sine graph is very clear, from sine 0 up to sine 90, this is how it goes. Then you can complete the remaining sinusoidal pattern. So it is from 0 up to 90 that you are concerned with. So these are the value from sine 0 to sine 90 that gives you the shift from 0 to 1. So we can see that the value keeps increasing steadily in the sinusoidal pattern up until 1. So I can say that as my angle increases from 0 to 90, then I'm moving steadily from 0 to 1. So at what point will I get to 85.4% of getting to 1? So which means that it is somewhere between 3/4. This is just like an approximation of 90. So that will be somewhere close to 1. Is this making sense? Hello?
Yes,
Okay.
Victor, yes.
Yes, it is.
Okay, so 3/4 of 90 degrees will give me the value that I'm looking for. However, if you do the math, we know that the angle that we eventually need in the rotation is not 90 degrees. It is times 2 of that angle. So that is where we are making use of the 180 degrees rotation. So in the code, all we need to look for, if you solve the maths completely or not even completely, you can just test run it. So how to write 3/4 of pi is now the next thing. So you do 3 times pi. So in Python, pi does not exist directly, so it is the non-pi. So we use this. So we are saying that now this is how to write the entirety of the 3/4 pi. Now 3/4 pi represents, in actual sense, what it represents is the angle of rotation is 3/4 pi. But if you want to calculate it with the sine value, it will be 3/8. That's half of this value, which is, yes, 3/8 of pi. So 3/8 of pi is what this rotation value we translate to. Because pi translates to pi over 2, but the rotation angle of 3/4 pi. But we're going to see this by the illustration. So we are acting on qubit 0. So again, if you want to see, okay, maybe then we can make use of what we have done earlier. So using the state vector now. So this will even save my time. State vector. So if I convert it to state vector just from what I've done earlier and try and see what is there. So if I say state vector dot draw, I don't need this, but I just want to, because sometimes we don't have the time to be calculating up and down. So just convert it to LaTeX since you know how it works. Then see, something is missing. This is a Python error. I forgot to add this. Then see what you have. Can you see directly here? So you already have the values here. Don't forget, these are just ordinary numbers. To make them probability, you have to square them. So this already, if you do 0.92 squared, you are having something closer to the value. Then if you do the square of the 1 on the 0, so here you can see the style of the probability. So again, now this is something complex. the numbers are scary. So just try to, but the closest one that is simplistic enough is this value. So if I want to show for that, the next thing is print the probability. So we can try and say, okay, how do I print probability from state vector? Since I already have the state vector here, so you can also, instead of drawing it, I can ask, these are all in the documentation. I ask for the probabilities, then probabilities dictionary. Now from the probability dictionary, is just you calling out the details. So everything now has been stored in what I call these probs. So I'm not printing it, that's why you're not seeing anything. So if I do print, so what am I printing? I'm printing the probabilities. So this is Python style probabilities. How do I print it? I'm printing it this way, props. So if I print, this is just like to make it well presentable. So this is nothing. So I'm just printing the probability. So the probability now, I haven't taken the square. Don't forget I said that. Now let me show this off. Okay, the best thing to do is let me split the cell so we can see it separately. So here I already ran the latex form. So if you compare it to the probability, it has already squared each of the coefficients that is in front of the zeros and one. So it's saying the value for the zero here is the 0.146 blah 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 that we can see here, and the value for the one is the other one on the right. So we can also show this like the third thing that says display on the block sphere. So the block sphere that we're talking about. So let me also create a new cell. Block. So block is multi-vector. Then I put the state vector there. Here. So if I run this plot multiple block square now, then I have something is missing. Plot block multi-vector. What is it saying? What is it saying? Unknown projection 3D. Oh, sorry, because I've already drawn it. These are things that Python will always give you errors for. Figure size. Then the errors with my matplotlib. Block multi-vector. Do I have Qiskit visualization? Qiskit. I think I did this already. Qiskit visualization. Qiskit this import Qiskit import. Is there visualization somewhere here? Yeah, from Qiskit visualization. Yeah, it's already imported. Import plot block multi-vector. So I don't know why this is plot block multi-vector SV. I don't know why this is not working. Unknown projection 3D. State vector probabilities dictionary.
Maybe my guess is from the values, the 3/4 that we use.
3/4? No.
Yeah, the QC.
No. No. It's I don't know. It's not that one is not an issue because it's supposed to plot directly what we are supposed to have. So it's somewhere. There's an error directly from somewhere that I'm not able to figure now. Because it's supposed to plot the visualization. Because yeah, it's showing the figure size, but it's saying unknown projection 3D. No. Now I cannot think of what the solution is at the moment. T vector. Okay, so I'll skip this for now. It's just to show it on the block sphere. So I'll solve this before sharing the next solution. Okay, then the multi-qubit operation and the entanglement, the how to do the what's it called? How to do the control gate, that's the C0 gate. So I think this is where we might be able to stop, but then I would have loved to generate more. Maybe I'll be more faster now. So here, the question here is like, we need to create a quantum that contains 2 qubits. So I'll be very fast. So this is QC equals to quantum circuit, then 2 qubits. Then create the Bell plus state. Now this is another concern in which the first Q0 is the control qubit. Now the Bell state, let me just quickly explain it. The Bell state here, which is the Bell plus, is just you having the approach of you having 0, 0, sorry, you having 0, 0 plus 1, 1, then both of them divided by √2. So this is the Bell plus state. And we have learned this before, when you have the 2 qubits gate, when you have the Q0 and Q1. And if you remember when we did this, to get this approach, it says the first qubit is the control qubit. So we first apply Hadamard gate to this bit. So when we apply the Hadamard gate, we are going to have the first qubit, the qubit 1 is still in state 0. So this is the starting point, 0, 0. The two qubits are both in 0, 0. But when we apply the Hadamard gate to the Q0, the one at the far right, don't forget. So that one alone switches to 0 plus 1 divided by √2. Do you remember this? Then the next thing is to use the Q0 as the control qubit. So we use the C0 gate. So this is where we are going. So we entangle it with the C0 gate such that when this is 0, it keeps this one at 0, which is having 0, 0 at this point. But when this is 1, it flips this one back to 1, then having 1, 1 at this point. So all we need to do is to design this circuit from the intuition that we already have about it. So to do that, the intuition is add Hadamard gate. And one of the things you can always do here is to always check if for the first timer, you can always check line by line if you are doing the right thing. So you have to have your draw section already here. So put it on qubit 0, then check. Okay, yeah, I'm on the right track just from this after showing the draw section. Then the only thing I need to do now is to use the C0 gate, which is just for me to do QC.CX, C0 gate. So I'm using the qubit 0 as the control, and the target is on qubit 1. So with this, I complete the structure. So we can see this directly. Then now draw the quantum circuit using Matplotlib. That I already did. Already, from what we can see, I already plotted the circuit. Then print the circuit state vector. By now, state vector is what is known to us. So we can just say SV equals to state vector, capital S, state vector. Then we put the QC in it. So here I have my state vector, but then if I want to display it as a print form, so print state vector SV. So, but most time, if you want to see your code line by line, you can split the two cells so that you can still have your diagram. Then the next line, you can then print your state vector. So the state vector here is just showing in this format. But if you want to have it, if you want to have it in a latex form like we did earlier, so you, instead of printing, then you draw. because the latest is a diagram. So what do I mean by draw? So you draw, you say sv dot draw AW, then you give it maybe latex so that latex can draw it in a nice format. So all these are just for you to see what you have. Then you show it in latex, then you can see already what you have in latest form. So I think question 5 will be a nice exercise. It's just you extending the diagram to 3 qubits. This was one of the things that we did years back in one of the challenge. So 3 qubits expansion. So I'm going to stop here. So the 3 qubit expansion will mean you should do something like this, 3 qubit where you have 0, 0, 0 plus 1, 1, 1 for the GSZ. Then you have everything divided by root 2 still. So here, what you need to do is root 2 or root 8. Yeah, I think it's root 2, so 50-50.
Should it be root 2 or root 8?
No, root 2 is root 2, 50-50.
Okay.
So we have all the qubits in 0, 0, 0, 1, 1, 1. So just the same. So the trick here is that once you understand how entanglement works, I remember then there are different ways to produce this same one, as I'm going to show you. So all you need to do is to have Q0, Q1, then Q2, all are in state 0. Then you have Adamat on this first one. So you use this one to entangle this second one. Then you can also use the same Adamat gate here to entangle the third one. Then you are done. Because what this Adamat will do, entangling the second gate, we do the same thing by entangling the third gate. Another way you can do that you can use like in the note. So it's just you knowing which one to use to entangle the other one. So here it says you can build the circuit, then draw method provide visualization in the format of text, MPL text. So you can customize the drawing with parameters such as reverse beat. So, sorry. So all of this will just be a case of, what's it called? Will just be a case of how well you want to customize, but I think I'm going to stop here. So just what I explained now, from what I explained now, so, well, for people that are really now smart in circuit plotting, you can just copy what you did before, because it's just like an advancement to what we have done before. So we have, oops, oh my God. So just copy this, I paste it here as my starting point, but now I need 3 qubits, so I change this to 3. I look at it, how does it look like? So I have 0 on this. So the next thing for me to do, yeah, like I said again, you can always check the state vector if you are doing the right thing. But the next thing to do is to use the same first, like I showed in diagram earlier, is to use the same first Adamat to now entangle the third qubit, which already gives you the state that you want to see. But then if you want to do like the method that we're given to reverse, so you can see that reverse bit is true. So reverse bit is just it's just for you to have the order, like you see, it's just for you to have a nice representation. Like if you don't want to have it as Q0, Q1, Q2, it's the same diagram, but reverse bit is always false by default. So you have it, the arrangement comes this way. So it's the same. So it's just like the note is saying that parameters such as reverse bit to flip the order, the qubit order. So what is happening from qubit 0 will now be happening on, sorry, have I done something? Okay, so what is happening on qubit 0, as you can see here, so you just have it's the same thing we have just done. It's just like you have Q0, Q1, and Q2. So this does not, but as you can see in the structure, it says draw the circuit with the qubit order reversed in the diagram. Q2 on top, Q0 on bottom. It's just like a design format. But how are we so sure that this is the right thing that we require in the GAZ state? The GAZ state, it was not explained in this exercise, but what it means is, like I explained earlier, what the GAZ state means is that you have 0, 0, 0 plus 1, 1, 1, then all divided by 2. And by now, I think you can verify if it is or not. So what do you need to do? You check the state vector. So you do state vector. So these are the ways you can, then you put your quantum circuit in it. Oh, so suppose that you don't want to affect your diagram, you can have a diagram, then the next state you have a QC, then you can say state vector dot draw. And then you draw it with latex. So I think alone this suffice. So as you can see, we have the required representation as needed. So time will not permit us to continue with all of the following, but you're going to see the solution. Also, you have access to them. It's just for you to understand how to use the code line by line. How do I, like this code now is saying create another 3-qubit GAZ. So with this idea, one of the interesting things that we did years back is to produce a GAZ with like 8 qubits. So the idea is that if you keep using this Hadamard gate here, at some point it doesn't get coherent again. So it is somehow not okay. Let me show something quickly here. Although I'm done. So I'm not reversing the bit. So I'm having the same thing, and I want to show that the state vector is the same. Now, what if I did not use the Hadamard up here? I use the Q1 to control the Q2, something like this. Look at what I have here. So I already entangled Q0 with Q1, and I entangled Q1 with Q2. Do I still have the same state vector? As you can see, I have the same state vector. So it doesn't change. But there are ways to just go about. Once you know what is going on, that okay, I use one to entangle the other one, I use the one to entangle that other. So this still gives you the same GAZ state. But it's just that by the idea of when we start talking about circuit depth and circuit depth, then you see that one of the procedure is more efficient than the other. In fact, somebody can decide to do something like this. In fact, one of the things that we try to look at then is that the Hadamard gate is placed on qubit 1. You can see, please look at the design. So see how I want to change it. The Hadamard is placed on qubit 1. Then I use qubit 1 to entangle qubit 0. Then I use the same qubit 1 to entangle qubit 2. So this is what we have. So Hadamard is in the middle. So I use one up, one down. I am guaranteed that I will still have the same state vector. And that is true. So this is just you saying, okay, how do I design my circuit? All of this comes into necessary usefulness when you have to consider the structure of the real quantum processing unit that you want to use. Say, for instance, in the quantum processing unit, entanglement is possible between the middle qubit and the third qubit. I don't know if I can show this. Are we still following? Let me just take 5 minutes to show us what I'm saying, IBM Quantum, because I remember that our speaker mentioned something like that yesterday. So in the IBM Quantum platform, is it this one? So we'll see that there are different structure of the qubit. Yeah, this one. Good. So if I can see just one. Okay, fine. So this is the diagram I'm talking about. So if, for instance, you are working with a design where you know that, so all these dot, they are the qubit numbers. And you can see that all of these qubits have different connections. So as you can see the qubit numbers shown, so if you are on this qubit, for example, if qubit 58, you can see the name. If qubit 58 is your qubit 1, because you are just designing your circuit blindly, but you want to fit your circuit to this particular quantum processing unit, it will be wrong for you to try to entangle qubit 58 to qubit 57. The distance is very far. So that is where you put the topology of your hardware into consideration. So if you entangle qubit 58 directly to qubit 57, even though in the original hardware they are just one number apart, qubit 57, qubit 58, maybe qubit 59. You look at the three of them, they were assigned just one after the other. So the way you have built your own circuit can just go and map 57, 58, 59. But there will be a lot of disaster because qubit 57 and qubit 58, even qubit 59, they are so much far apart in the design of the hardware that you want to use. So this is where transpilation comes in. So you have to, your design is correct from the scratch, but that design will now have to be reconfigured such that it will not map 57, 58, 59, but your qubit 0 on your own design, you can now assign it directly that qubit 0 should be qubit 57 in my hardware. My qubit 1 should be qubit 67 in my hardware, and my qubit 2 should be qubit 47. And in that order, you will see that the middle qubit can easily entangle itself with the up and down. So these are the things you look at when you want to do real research, so that your design is directly focused on the hardware. So these are things that people also do. So you have designed it correctly, yes, but you have to now transform your design to the hardware specific, to be hardware specific, so that you can be sure that the entanglement that exists in your real circuit is the same as the hardware. So these are the things that you do when you try to study the topology of the hardware. So I think I'm going to stop here tonight. So, but we were not able to get to hardware. How do we transpile our circuit to the original hardware? So which hardware are we working with? Which one do we have access to? Because each of the hardware has different designs. So you cannot just use the same algorithm, the same circuit that you have produced. So IBM already has some of these things that AI is doing for them. So AI can directly transpile, we call it transpilation. You directly transpile your circuit to the choice of your hardware. And this also you can do manually, but it's not so easy. So this is another circuit design. So this one I've worked with before. So you can see the numbers of your qubits. So you don't say because, yes, this qubit, there are 127 qubits in this particular design. So even if your design is correct, you have to ensure that you put this number of qubits in mind, so that your qubit 0, this is the actual qubit 0. So if you are mapping the same way, 0 to 0, so this is how it's going to work. So qubit 1 to 13 are on a linear topology, but qubit 14 is far from qubit 13. So you don't entangle 13 and 14 together in your circuit. So it's just an idea of what transpilation is all about. So it should not be easy for us to be designing our circuits with the hardware in mind. But what IBM is doing as part of their research work is that you design your circuit, then we have our internal algorithm that will convert whatever circuit you produce to the hardware in such a way that all the entanglement that exists in your circuit will be compatible with the hardware topology. Okay, so I hope we have gained something in this session. All right, so I'm going to stop here. If there's any question or further explanation that is necessary, please let me know.
So thank you, Victor. It's a beautiful time, and I quite follow. But I want to request that tomorrow we can start from this last one. Maybe we can create a dummy circuit like this. I mean, on our own by interaction, so that we can see the beauty of this kind of circuit. Then the second thing is, I hope we will get this immediately. We won't wait till tomorrow, so that before tomorrow we will not forget what we have done. That will be very key. Then